Hi everyone, welcome back to our second lecture. So Shehan is going to tell us more about the combinatorial atlas and yeah, all yours.
Okay, thank you very much for the introduction again, Anna. And also, I would like to thank everybody again for coming today. So today is a continuation for this lecture for the log concave poset inequalities. And today we'll be going to talking about the improvement to Mason's conjecture. Okay, so on the first day, we talk about the Mason's conjecture for graphs. So today we want to talk about something a little bit like epsilon more general, which is for matroids. And for recap, a matroid is a combination of two things. First, you have a ground set that we will label always X. Today, our X is always be a finite set. And there will be a collection of subsets of the ground set that's called the independent sets. Okay, it's labeled by I. And this independent set will satisfy two axioms. The first one is called the hereditary axiom. It says that any subset of an independent set, so here T is the independent set, any subset of independent set will again be independent. Okay. The second property is called the exchange property, which says that if you have two independent sets S and T, and you know that one set is smaller than the other, then you can always find another element in the larger set, put it into the smaller set, and the resulting set will again be independent. Okay. So these are the two properties that define a matroid. And one of the maybe two of the most famous example of matroid is the graphical matroid and realizable matroid. Graphical matroid is when when the ground set is a set of edges of a given graph. Let's say the graph is connected, and the set I is the set of forests, set of edges that form a forest. This is the example that we focus on the day one. Okay. And today, other than the graphical matroid, we will also study the realizable matroid. This is when the ground set is any finite set of vectors over a field F. Uh, in fact, most of the time today, our F will be a finite field. So like F2, F4, FQ, and so on. And independent set is, pardon the pun, is a set of linearly independent vectors over the same field. Okay. Okay. And so the question that we want to discuss today is the Mason's conjecture from 1972, which says that let M be a matroid, any matroid, can be graphic, can be realizable, can be anything. Let AK be the number of independent set of size K. Okay? And back then, Mason conjecture log concavity in the three different level, which now we call Mason 1, Mason 2, Mason 3. Okay? And the first one is the normal log concavity, and the last one is now what we call the ultra log concavity. And actually, I went to check the paper for this Mason's conjecture, and it seems like the reason why Mason actually wrote these three different conjecture rather than just one of them is because back then they are not even sure. They were not even sure that the first one is correct. Okay? So that's why I think Mason tried to hedge his bet and say that, okay, we have three conjecture, one, two, three. Maybe one of them is wrong, maybe one of them is wrong, the other one is correct. Okay. And previously, we proved the Mason 2 for graphical matroid in day one, okay, by using Combinatorial atlas. And today, our goal is actually to prove Mason 3, again, by using Combinatorial atlas for all matroids. And furthermore, if we have enough time, we will go for Mason 4. So it turns out there is actually a stronger form of log concavity that Mason did not conjecture, or Mason didn't see back then. That is our goal for today. Okay, any questions so far? Everybody happy? Okay, if everybody happy, then let me continue. And again, on the previous class, on the previous day, we proved the Mason 2 for graphical matroid, but actually that proof still work for all matroids. So today, maybe as a quick recap, let me just go through the same proof again, but now we prove it for all matroids rather than graphical matroid. Okay. And the idea for the proof is the following. First, we define this thing that we call the independent words. This is a word where all the letters are coming from the ground set of the matroid. And we say that it's independent word if you look at the subset formed by the omega 1, omega 2 up to omega k. So the subset formed by the letters of the word. We say this is an independent word if the subset is now an independent set of the matroid. For example, if your matroid is a forest matroid, is the graphical matroid, E1, E3, E2, this is an independent word because if you look at the subset, if you look at the graph formed by the three edges, this has no cycle. Therefore, by definition, it is an independent set for the graphical matroid. And notice that here, E1, E3, E2, and E1, E2, E3 are considered separate words. Okay? So order does matter for the independent word. That will be important to get one of the constants in the Mason's conjecture. And as a non-example, E1, E2, E4, so this one, is not an independent word because it has a cycle, it's a three cycle. E2, E4, E2 is also not an independent word because here you see that they form a two cycle. You have two parallel edges. That's why in general, in particular, your words will always be simple in the sense that there are no repeating letters. And oh, by the way, on the first day, we call this forest word rather than independent words. Okay. Okay. And what we are going to do is that by using this information, we are going to build this thing that's called the independent matrix. So let us enumerate X, the ground set, as X1, X2 up to Xn. K is fixed between 0 and n. Okay, this is just because otherwise the Mason's inequality is actually trivial. Independent matrix is a n plus 1 times n plus 1 matrix. The matrix is labeled as I2. This is because it's going to be used for Mason 2. For Mason 3, we will use the matrix that's called I3. For Mason 4, it will be matrix that's called I4. Okay. So I2, this is defined, the entries for I and j, when I and j is less than m. This is number of words of length k plus 1, start with x1, xi, ends with xj. Okay. And oops, this is, I forget to update this. This is m plus 1. This is m plus 1, m plus 1. Okay. And when your last entry is m plus 1 of your entry is m plus 1, there will be number of independent words, length k, only starts with xi. You don't have condition on the ending number. And when it's m plus 1 times m plus 1, this is simply the number of independent words of length k minus 1. No condition on the starting point, no condition on the end point. Okay. So let me get some water. Okay. And for example, this is the independent matrix for the graphical matroid for this graph. It's a 5 times 5 matrix because this matrix has 4 edges. So 4 plus 1 is 5. And k is equal to 2 here. So you see that the entry correspond to 2 and 3. This is the word start with E2, ends with E3 because this 2 and 3. And the length is 3 because k plus 1 is equal to 3. 2 plus 1 equal to 3. Okay, entry 2 and 5. This is now a word of only start with E2 because there's no condition on the ending words. And 5, 5, this is the one where you just simply count all of the words of the length 1. That's why there are 4 of them. This is the how you get, this is the combinatorial interpretation for this matrix. Everything clear with the example? Okay. Okay. And now the thing that, remember that the thing that we want to prove to get all this log concavity will always be the hyperbolic property. This is the property such that if you take the matrix M, take the inner product with x and y square, this will be greater than the inner product of x with itself and inner product of y with itself. This property is the one that we will use to get log concavity. But whenever we want to try to prove this property, it's usually easier to prove this one, which is what is called OPE, which is equivalent to hyperbolic property, which says that the matrix M has at most one positive eigenvalue. Okay. It's known that this property is equal even since like 1920s, like since the time of Alexandrov. And the idea is always to interpolate between these two. That when you want to prove log concavity, you use the first one. When you want to prove the property that this matrix has this property, you use the second one. Okay? That will always be the philosophy of this the proof. And let me say that maybe one of the most maybe let's say the proposition or like the theorem before we prove log concavity, we'll always be saying that our independent matrix will be satisfy the hyperbolic property. We'll prove this very soon, maybe like in 5 minutes. But let me just mention how this theorem implies Mason 2. This is because take your M to be the independent matrix that we defined earlier, X to be the vector, all the entries are equal to 1 except for the last entry. Y is the same except that you reverse the order. The first n entries are 0, the last entry is equal to 1. Then by definition, by the combinatorial interpretation of M, you see that xmy is equal to k factorial times ak. Ak is a number that appears in the Mason's conjecture. K factorial, because remember, we are dealing with words, not with the subset. That's why given an independent subset, there are k factorial possibility to make it into a word. That's why you get the k factorial, the same reason behind k plus 1 factorial and k minus 1 factorial. So now you put this into the calculation, the 1 plus 1 over k then follows from these three constants. That is how independent matrix theorems imply Mason 2. Okay. Up till here, everything clear so far? Okay. Okay, and now let me explain how we prove the independent matrix theorem, which is by using what we call the independent atlas. So here is a quick recap. A combinatorial atlas, this is simply a collection of D plus 1 matrix. It will be non-negative for simplicity. It will be symmetric. Okay. M0 will be the parent of atlas. M1, MD will be the children of the atlas. And there will also be an extra vector that's called H. This is also part of the input. And the atlas that we want to use to prove this independent matrix theorem, we will need to define what is a matroid contraction. This is the equivalent for the graph contraction for the matroid, where given an element x of the matroid, M over x is the matroid where the ground set x prime is the one where you remove the element x, and the independent set is the one such that when you add x into S, this set is independent in the original set. This corresponds to the contraction operation for the graph, but now generalized to all matroid. Okay. And similarly, just like how in graphs we have the definition for loop and parallel edges, we also have the same definition for matroid. And the definition is that a loop of a matroid is the one such that you put the element into as a set, that thing is not independent. Okay. In particular, it means that you can simply remove the loops. And given any two proper elements, the one that's non-loops, we say they are parallel if the subset that containing both elements are not independent. Okay. And in the case of graph, this actually loop correspond to, well, a loop edges. Parallel elements correspond to parallel edges in the graph. And we say that a matroid is simple if it has no loops, has no parallel elements. Okay. Okay, and any questions so far? I hope I don't talk too fast. Okay. Okay. Now finally, now I can, using that definition, I can define independent atlas. So fix a number t strictly between 0 and 1. Fix k to be between 2 and m. The reason why I start with 2 rather than 1 is because the case k equal to 1 will be the base case. And that case are usually trivial. That's why usually we start with k greater than 2. I define my independent atlas to be the parent will be the interpolation between imk and imk minus 1. Okay, this is just for some technical reasons. The children will always be the contraction of the matroid with respect to element xi. The k always become one smaller, become k minus one. That's how we are allowed to apply induction. The last children MD will be the one you don't do any contraction, but the number k become k minus one. That still apply. Okay? And by the way, in the first day, we call this forest atlas when it's for graphic matroid. But today, because we are now dealing with general matroid, now I call it for the independent atlas. Okay, and any questions so far about the definition? Everything clear? Okay, everybody happy? So let me continue. And one important property of this atlas is this thing that's called the children-parent principle, which says that if your atlas satisfies 5 technical properties, we prove those 5 properties in the first day. Today, so that I don't bore everybody, we will not do that calculation again. But let me just mention that they are all like more or less routine. They are all properties that are more or less easy to check. And the idea is that suppose that you already know that this property holds, and you also know that all of the children satisfy hyperbolic property. Then you can use induction usually to assume that this is true. Then it follows from this principle that the parents will also satisfy the hyperbolic property. Okay? That is how we'll always play this game. We first prove the base case, then we assume by induction all of the children has the property, all the children have COVID. Then the parent will also have the hyperbolic property. Okay. Okay, and sorry for all of this setup, but now we can prove the independent matrix theorem. The idea is as following. We will use induction on K. And the best case will be K equal to 1. And without loss of generality, you can assume that the matroid M is simple, that it has no loops, no parallel elements. In this case, your matrix will be equal to this matrix written over here. It is an explicit matrix. You can put it into Sage, run this thing, and it will tell you that these are the eigenvalues, which is that the first entry is positive, the last entries are all strictly negative. This is important. They are all strictly negative, no zeros. Okay. In particular, this means that they all satisfy OPE. In particular, it satisfies the hyperbolic property. So this proves the base case of the induction. Okay. And now assume that K is greater than 2. By induction, all of the children got the hyperbolic property. Then, by the children to parent principle, the parent also get the hyperbolic property. But by definition, M0 is equal to this matrix over here. And because hyperbolic property is preserved as you take t goes to 1, as you take the limit, that's why as t goes to 1, the matrix I2MK also satisfies the hyperbolic property. That is how we prove the independent matrix theorem. And once you put everything together, that is how we prove the Mason tool for the Mason tool for all matroids. Okay. Up till here, are there any questions? Yeah, let me get some water also. Okay. Now, since that everybody is happy, let me mention that. So today, our goal, at least maybe our first goal, is to show how can we go by using the same proof more or less, to prove something a bit stronger, which is the Mason tree, or actually the strongest version of the Mason's conjecture, where you have the extra constant of 1 plus 1 over n minus k. That will be our goal for the next 10 minutes. Okay. Everybody ready for how we prove this? Okay. So, of course, the main question to ask is that what part of the proof can we improve? How do we get this Mason tree from what is actually not optimal in our previous proof? Right? And to do that, let us look back at our proof for the base case. Notice that we have this D times D matrix, right? And also notice that when we do the calculation, this matrix has eigenvalues approximately this value. I claim that there is a room to improve here. The reason is as follows. Suppose that I change the matrix. Let's say that the last entry, rather than putting exactly 1, I put 1 plus epsilon. In this case, as long as the epsilon is really, really, really small, then you see that it only affects the first eigenvalue and the last eigenvalue of your matrix. The rest is still equal to -1. And therefore, when epsilon is really, really, really small, the first eigenvalue is still positive. The last eigenvalue is still negative. And therefore, this matrix will still satisfy OPE. It will still satisfy the hyperbolic property. But by changing your matrix to this definition, you see that you improve your log concave inequality from the previous one with 1 plus 1 over k to the one with extra 1 plus epsilon. This is the room for improvement. This is the room of improvement that we can use to go from Mason 2 to Mason 3. Okay. Any questions so far about the idea that this is where we can get better proof? Okay. Now, so what this means is that in order to really prove Mason 3, we need to change our definition for independent matrix. That's why we call this I3. Okay. Independent matrix for Mason 3. It is the same definition as before. Let me change this to n, except that now you add a new constant n minus k minus 1 factorial, n minus k factorial, and n minus k plus 1 factorial, depending on the type of your depending on the type of your entries, or depending on the type of your index. And notice that by this new definition, we will, let me say this first. We will also assume that, we will also want to prove that this matrix satisfies hyperbolic property. And I claim that if this new matrix satisfies hyperbolic property, then it will also imply Mason 3. In the following way, again, you play the same game as before, but instead of taking M to be equal to I2, now you use I3. Then by definition, XMY, XMX, LIMY is the same number for before, except that now you have this extra constant n minus k factorial, n minus k minus 1 factorial, and n minus k plus 1 factorial. Okay. Now, when you plug this into the hyperbolic property, these three constants, they all cancel each other, and they give you the 1 plus 1 over n minus k in the Mason tree. This is how we prove the strongest form of Mason's conjecture, assuming that we have in the mathematics theorem. Okay. Up till here, is everything clear so far? Okay. Okay. And if everybody's happy, then let me just quickly prove the Mason tree now. And the idea is more or less the same thing you have guessed. We use more or less the same process before. Again, we do induction on K. Again, we assume M is simple. But now, the only thing that changed is that I3 is not the same matrix as before, where all of the entries equal to 1. Now, the entries can be different depending on the location of the index. But the good news is that even with this definition, you can still put it into stage. The stage will still tell you that these are the eigenvalues. Notice that the first one is equal to positive number. Second one is 0. The rest are all negative. The fact that you get a 0 as eigenvalues, that is a sign that this inequality cannot be improved anymore. Because if you again remember, if I do my trick with epsilon, then suddenly this matrix is not hyperbolic. It has now 2 positive eigenvalues. That is why this is the best you can do. Okay, at least for now. Okay. And therefore, but regardless, you still only have 1 positive eigenvalues, right? Because the rest is non-negative. By definition, this matrix still satisfies OPE. In particular, it still satisfies the hyperbolic property. So the base case still works. And then the rest, you simply do as before. You assume k greater than 2. You build the same atlas, except that rather than taking I2, now you take everything to be I3. And then the rest of the proof works as before. By induction, the children satisfy the hyperbolic property. Then the parents satisfy hyperbolic property. Then you take p goes equal to 1. Then you prove the adiabatic matrix theorem for all values of k. Okay. So the only thing that changed is the definition of the matrix. And maybe checking the best case becomes a bit more complicated. But once you do that, you got everything. You got your Mason tree. Okay. Up till here, I think it's actually a good point to ask question now if while I'm drinking water. So feel free to ask any question now before we continue. Okay, no, everybody happy? Okay, now if everybody is happy, recall that the title for today's today's lecture is Improvement to Mason's Conjecture, right? So now that we have finally gone to now that we have finally proved the Mason tree, or like the strongest form of Mason's conjecture, our goal now should change to show that this inequality turns out that it can be improved even further. Turns out that not only that Mason tree is right, we actually now know there's inequality that's even stronger than what Mason has stated, that what Mason has envisioned 50 years ago. That is what we call Mason 4, for lack of better name. Okay. And hopefully there will be no Mason 5 in the near future. Okay. And the statement and the proof of Mason 4 is actually a bit more complicated. It's a bit convoluted. So let me just, for now, maybe as a proof of concept, let me state only the Mason 4 for the case of graphical matroid and when k is equal to v minus 2, where v is number of vertices. Of course, we have one for all matroids for all value of k, but just for simplicity, let me state it for this case first. And in this case, I claim that the constant 1 plus 1 over n minus k can actually be improved to the constant 3 over 2. Okay? And this is the same constant that we saw in the day 1. That is in our last episode preview. Okay? And I claim that this inequality is strictly stronger than Mason 3 because of the following reason. First is, of course, because 3 over 2 is better than 1 plus 1 over n minus k. But even not accounting for that, Mason 3, if you take the limit as your graph goes to like an infinite graph, the constant that you will get is equal to 1, while for Mason 4, your constant you get is 3 over 2. So it is a strict improvement from the asymptotic perspective. Okay. And today we are going to prove the Mason 4 by using Atlas. But before I proceed, are there any questions? Yes? No? Yes, Jason?
Is cup
Yes, yes, sorry. I think I don't I think you got cut out. So
okay? Is kappa fixed or
cup
ranges?
in this example, kappa is fixed. But I think in around 10 minutes, we will see the version where kappa is not fixed. Okay. Thank you. Any other question? Okay. And now let me just mention quickly how this part of the proof can be improved. Okay. And previously, we claimed that, well, we improved this by changing the matrix I2 to I3. And you notice that this thing already has an eigenvalue 0, right? So this kind of imply, or this is intuitively is clear, that there's no room for improvement anymore for this matrix. So you should not expect you should not expect that you can prove a stronger version than Mason tree. However, note one thing that's actually that I didn't say before, which is that this matrix is actually the worst case possible. In most of the time, you never see this matrix as your base case. In particular, for graphical matroid, this matrix never appears. And therefore, we will see it in the proof that this matrix never appear. And therefore, we can be a bit more bold. We can be a bit, we can try to have a definition of independent matrix that is actually stronger. The resulting of doing that is what I call the independent matrix for the matrix I4. This is the matrix where, again, it comes from I2. The definition is the same as before, except that now, the last entry here, rather than putting k factorial and n minus k factorial, I just put number 3 over 2. This 3 over 2 will be greater than the improvement for Mason tree. Okay. And now, again, as you might expected, I claim that this matrix satisfies the Mason tree. It satisfies the hyperbolic property. And if you use this matrix and put it into our tool as before, you will see that once you do all the calculations, at the end, the number 3 over 2 will come up rather than the 1 plus 1 over n minus k. And that implies Mason form for graphical matroid. For general matroid, the definition, the number will be different. Okay? But otherwise, the proof remains the same. Okay? And now without delay, let me just show you the proof of this in the mathematics theorem for the improvement. And the unfortunate, the thing is that the proof for the Mason 4 actually becomes a little bit more subtle. First thing that changed is that rather than doing induction on K, we do induction on number of vertices. You will see why soon. So base case is V equal to 3. Again, with law of generality, you can assume that the graph is simple, because otherwise we can always reduce to this case. And the important thing, when you have a graph, you have 3 vertices. How many edges can you have? Well, at most you have 3 edges. We choose 2, right? This means that your matrix cannot be the giant matrix that we saw from before. The one, which is this one matrix. This matrix cannot appear on the graphical case because the size is too big. Instead, the only 2 possibilities are either, where is it? Let me go back first. Either this matrix or this matrix. You do the calculation for both, you see that the first one has 3 eigenvalues, the last 2 is negative, and the third one, you see 1, 0, which is a sign that this thing cannot be improved anymore, and the other 2 eigenvalues are negative. In particular, this matrix I4, at least for the base case now, will satisfy the hyperbolic property. Okay. And now, as before, we will use this information to build an atlas and use the children parent principle to prove it for all, to prove that it's true for all values of V. And here, the thing is that there's actually another subtlety. Notice that in the definition of the atlas, this matrix is I4, this matrix is I2. This is intentional. This is not a typo. This is because if you put this I2, let's say you put I4 here, what will happen is that remember that there are 5 properties, right? There is this INH, the independent inheritance property, decreasing property, and so on, that atlas needs to satisfy. If you change the I2 to I4, that property will be false. You really need it to be I2. On the other hand, if you change this thing to be, all of this to be I2, then you don't get any improvement. Therefore, this now becomes a game for Mason 4. It becomes a game to know exactly what thing to improve, what thing to not improve. Okay? The good news is that we actually don't need to guess. because we actually, with these tools, we have so many, the setup is more or less rigid, that whenever you want to do improvement, the setup will tell you what kind of changes you can make. So this part is actually not so the hardest part, maybe the hardest part is to realize that you can improve, not what to improve. Okay. But in any case, that is what you do. You, depending on the situation, one of them you choose I4, some of them you choose I2, but the rest of the proof is the same. By induction, all of the children satisfy hyperbolic property. Then you take t goes to 1. Then finally, you get the conclusion that your matrix satisfies the hyperbolic property. And after that, you put in all the calculations. In the end, you get that you get the Mason 4 for the graphical case. Okay. And one more thing I want to mention at this point is that another advantage of doing atlas is that when you can prove an inequality, it also follows by just maybe one extra lemma that you can get the equality condition. In this case, the equality condition for the graphical matroid and for simple case is that this is equal if and only if the graph G is a cycle graph. In any other case, this constant is in fact not, you can get a better constant. And if you know more, the more you know about your graph, let's say you know that this graph has no triangle, this graph has no, does not have this, what do you call that? Has like a limited bounded number of degrees, then this constant can be improved even further. Okay. Up till here, are there any questions before we go for the Mason 4 for all matroids? Okay. Okay. Everybody happy? Then let me continue. And let me now, let me first apologize first that for Mason 4 for all matroids, I will not present the proof. I will just state the theorem. But I just want to say that the proof more or less works the same. More or less works the same as the proof from before for graphical case. Only that you need to state everything in terms of independent set rather than in terms of forest. Okay? But here is the statement for Mason 4. And to do that, I need to define what is a parallel classes. So remember that two elements of a matroid, we say they are parallel if the subset containing the two elements are not independent. It's easy to check that this defines an equivalence relation on the elements of the matroid. Okay. And a parallel class is simply an equivalence class of this relation. So for example, in this graph, there are three parallel classes. One, these two edges count for one class. This one count for one, this one count for one. Loop edges is not counted because they never appear in your independent set. Okay. Now I want to define a parallel number, which is first, given any independent set S, you apply the contraction to this independent set. Okay, so you get a new matroid MS. The parallel number of S is the number of parallel classes of this independent set. Or intuitively, you can think of it like this. This number is the number of edges or the number of elements of the matroid after you do the contraction and you don't count the multiplicity. So if there are two parallel edges, you count that as one. For example, in this graph, let's say S is this 4 red edges. After the contraction, you get this graph. This graph has 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 edges. Because even though you have 6 edges here, the 2 edges count as one class because they are parallel to each other. Okay. Now I define the parallel constant of the matroid. This is the constant where you take all of the independent set of size k, you calculate the parallel number for each of them, you take their maximum, or if you want, you take the tropical sum. If we give you a number, I claim that this number is what appears replacing n minus k in the Mason form, in the Mason tree. And it can be shown, it's not hard to show, that the parallel number, the parallel constant, is always smaller than n minus k plus 1. In particular, implies that Mason 4 is always better, at least as good as Mason 3. This is what I claim to be the improvement of Mason 3. Okay. And of course, if I claim something to be an improvement, I need to show an evidence, right? Why this is an improvement. So let us see what is the improvement for a different matroid. First, the first situation is when you don't know anything about matroid. I just tell you that it's a matroid. I don't give you any extra combinatorial information. Then in this case, yes, the best you can do is that you just guess this number is 1n minus k. This is the same as Mason tree. No improvement can be made. However, if you know that this graph is a graphical graph, it's a graphical matroid, and let's say k is equal to v minus 2, then you see the improvement that we saw in the beginning, that we saw for graphical matroid, the number 3/2. In general, the improvement can be very small and can also be very large. For example, for realistic matroid, the improvement is this number. Asymptotically, they are the same as the Mason tree. But if you do this for another matroid that's called Steiner matroid, let me not explain what it is because of time restriction. Then this improvement, as you take the matroid, it goes to infinity. Mason tree will give the ratio to be equal to 1, while our improvement gives the ratio is equal to infinity. So it'll be a much better improvement for Steiner matroid. Okay. And in conclusion, what I want to say is that, well, we have improved Mason 3 to Mason 4. And in order to maybe not guarantee, but at least to make myself feel like a bit safe, that Mason 5 probably will not appear anytime soon. We will also give a matching equality conditions for this inequality. Okay. And rather than stating the inequality condition, let me just state when is equality achieved for this Mason 4. Okay. And somewhat surprisingly, at least in the beginning, we actually thought that there will be only one equality case. But turns out that there are actually many situations when this inequality is strict. First situation, when M is a free matroid. This is when every subset of the ground set is independent. In this case, then yes, the Mason 4 is always equal. That this is one of the equality cases. Another case is when M is graphical matroid, when the graph G is cycle, when K is equal to V minus 2. Again, you see that this is an equality cases. Another equality cases is when M is realizable matroid, and the independent set, it contains all vectors, all m-dimensional vectors over the field FQ. It's another equality cases. And then there's also Steiner system matroid, and then there's also many other cases that I do not write because I simply run out of space. Okay. But in conclusion, all of that condition, they are actually a special case of this equality condition that I wrote over here. We say that if and only if condition, if and only if equality condition, if and only if condition for when equality occurs in our Mason form. The condition is a bit convoluted, and I used to actually worry a lot that why is it that this condition is so convoluted, that we spent some time trying to find an easier way or maybe equivalent condition that is easier to state. Okay, but recently I learned to stop worrying about it because of two reasons. The first reason is that it turns out that it is inherent to this question that the equality condition must be complicated. That's the first reason. The second reason is that we learn how to use the fact that you have convoluted equality condition to prove existence or non-existence of combinatorial interpretations. This is something that Igor will discuss more in the fourth day on this aspects of combinatorial interpretation. Okay. Anyway, in conclusion, what we have done today is that we are focusing on combinatorial atlas with the application to Mason's inequality. On the next class, which is on day 3 and maybe day 4, we will discuss on Stanley-Posset inequality. Also now we apply it to a completely different stuff. And at the last day, we will also discuss another inequality, which is called the Stanleyian matroid inequality. That's related to the Mason inequality. This one will be done by Eager, and you will see exactly what I mean by equality condition implies combinatorial interpretation. Okay, and I think that is all I want to say for today. Thank you very much for listening.
Thank you so much. Any questions?
Oh, I saw one question in the chat. Let's just say thank you.
No, no questions. I actually have a very not related, not really related to the atlas, but you mentioned something interesting about like the Mason's conjecture, and then you mentioned that they put out 3 conjectures because they don't know even the first one is correct. But actually the second and the third one are even stronger. So how come they didn't even trust the first one and then they would try to find the second and the third one? Do you know the history of that?
I a little bit, yes, but okay, that's a very good question. But so actually what we do is that I went to check this paper, the journal where they published the Mason's conjecture. In fact, it's not a journal, it's a conference proceedings. And it seems like in that conference proceeding, they state many log-Fourier conjecture, not just the Mason's conjecture. There was I think the Heron-Protawas conjecture, and also the other one, the Delson's conjecture, were also published there. And in all of those situations, they all write it as 1, 2, 3. And it seems like the reason is the following. Because at that time, they do not even know to prove log concavity, but they also notice that even assuming this inequality is true, that this inequality, they cannot find the equality condition. They never find equality cases for the first one. And the one where they can find is the third one. This is the one when the matroid is free matroid. And that's why they kind of guess that if 1 is true, then 3 is also true. But then they are like it's like they try to hedge their bet by saying that 1, 2, and by splitting it to 1, 2, and 3. Another reason is that sorry, yes, Anna.
No, I'm just saying I see.
Yeah, actually, another reason I want to state is that in between this time, there is actually a paper 1981 by Stanley where he proved this one, the first one, only for a special case of matroid, like only for one special case. Special case like is those matroid that can be written as a genotops. And in that situation, he also mentioned that his proof works for Mason 1 but not Mason 3. And that I think that's one of the reasons at that time where people believe that maybe Mason 1 can be true but not Mason 3. Of course, now we know all 3 of them are true, but at least back then it is a bit it can be it is within reasons to guess that maybe one is to state it as 2 separate conjecture. Thank you for the nice question.
Yeah, I also have a questions on how did you discover that when you're trying to prove the 4, you have to use the TI4 plus 1 minus TI2? Like, did you just try different things or
That's a good question. Let me just go back to that slide. This is the slide. Yes, and the idea is mainly because we just know that if I put I4 for both, then the proof will fail. Then this property
Right.
that we call the decreasing property and actually the INH, inheritance property, the one that we need to prove the atlas will be going to fail. So we need to find one definition that works. And the idea is simply that, okay, we know our goal, right? We want to prove I4. And then after that, we just backtrack from there. We want to put something here that allow you to still have the property. Turns out I2 is already enough. If I2 is not enough, we will try I3. If I3 is not enough, we try I3.5. But I2 is enough.
I see.
That is yes. Any other question? I hope this answers your question.
Yeah, I'm just curious because I think to me this is such a powerful tool, and I'm trying to understand, like, if I'm trying to use it in other situations, like how am I going to, if I end up struggling in any situation like this, like how do I know how to improve the proof or modify the proof? And that's very helpful for your answer.
Thank you so much. Thank you so much for answering a very good question.
All right. If no other questions, let's thank the speaker again.
Thank you so much for hosting me for today. Let me stop sharing.
So we will have our next lecture would actually be next week, right?
Yes, on Tuesday.
Next Tuesday. All right. So the recording will be posted on YouTube soon, and I will see everyone next week. Thank you so much.
Bye-bye.
Bye.